Hi, welcome back. My name is Attila Börös. This is the sixth lesson in our solar energy course and the second in the solar energy to heat conversion topic. In the previous chapters, we learned about the sun, the sunlight, its effects, the history of using the solar energy. The last one was not enough for the what can we do with the solar energy subject. I was talking about the methods for using solar thermal energy, active, passive energy usage, the different type of solar energy collectors, and water heating applications. Now we will cover the solar air heating applications, medium temperature solar collectors like solar cooking, and finally the different power plant types using concentrated solar power. These are high-temperature solar collectors. Until now, we were talking about solar heating systems using some kind of fluid to transfer heat. In the next couple of minutes, we will check the systems where the solar energy warms up not fluid, but air. Solar air heaters are mostly used in domestic space heating. Solar air heat is also used in process applications, such as drying laundry, crops, for example, tea, corn, coffee, and other drying applications. They are easy to build, but they are not as efficient as water heat collectors and thus require a large area for the required heats. There are plenty variants of solar air heaters. In the most common setup, the collector draws cool air from the house, heats it, and returns the now heated air to the living space. This is called a closed-loop system. The other type of setup is called an open-loop system. Open-loop systems draw in cold outdoor air, heat it, and then transfer it to the living space. For residential systems, closed-loop systems are your best. There are plenty variants of solar air heaters. In the most common setup, the collector draws cool air from the house, heats it, and returns to the now heated air to the living space. This is called a closed-loop system. The other type of setup is called an open-loop system. Open-loop systems draw in cold outdoor air, heat it, and then transfer it to the living space. For residential systems, closed-loop systems are your best bet, but the open-loop system in combination with heat exchanger in a house airing system is better option. Among the plenty variants of solar air heaters, some are quite simple, like this is the right side. This inside perforated black metal box is fastened directly to a building exterior. A small computer fan pulls outside air into the slots. It is warmed up, and the air is pushed through a pipe to the interior of the building. There is a small computer inside with sensors measuring indoor and collector temperatures. The small phone is operating only when the air temperature in the collector is higher than the indoor temperature. But there are more complex systems, like one on the left side, where the collector is combined with a heat storage, like concrete or water. Store the energy is not an easy task, but there are some possibilities. Normally, storing the solar thermal energy is handled with thermal mass inside the home. During the day, the thermal mass is absorbing the heat provided by the solar air heating system. At night, thermal mass will slowly radiate the heat it collected into the living space. The more thermal mass, the longer the home will stay warm after the sun sets. Storage can also be handled with rock bins. A blower circulates the warm air from the collector to a bin of rocks, which will absorb most of the heat. When the home requires heat, it is pulled from the rock bin. Here you can see a DIY solar wall collector. The beer can solar heater is easy to make as well as eco-friendly. You can heat your home and lower your heating bill with an easy-to-build solar heater made out of empty beer cans, cardboard, and cellophane wrap. The beer can solar heater works on the same principles as the passive solar heater. The cans absorb the sun rays, causing the air in the cans to heat up and rise. As the hot air rises, cool air is pulled from the floor to be heated again by the sun. You will see a whole video later in this course about the not too complicated but very useful system. You can do it yourself, including this application as well. So now just quickly evaluate the pros and the cons of it. Let's see the pros first. You can generate clean thermal energy with leftover soda cans. If you like the feeling of building something with your own two hands, this is a good outlet for your love to tinker. You can heat a small space for the cost of a few hardware software supplies, plus cans you would toss in the recycling bin anyway. It is a fun project with a practical use applications. Everything has two sides. This is also not an exception. But actually, the cons are not always cons. It depends on the point of view. Let's see them. They only generate a small amount of heat, not electricity. There is no easy way to connect them to a battery or store the heat energy. You have to use the heat energy you generate right away. It is a time investment, and you must be careful not to cut yourself with the tools and sharp metal of the cut cans. Most likely, it will not look pretty, but actually most of the cons are the same with the factory-made devices. Drying is an excellent way to preserve produce, but exposing fruits and vegetables to direct light can cause vitamin loss. This design relies on the indirect solar power, meaning the drying food is not exposed to the sun, but instead to solar heated air. The solar dryer takes advantage of the natural process of rising hot air to operate efficiently without any electric fans. As you can see in the detailed drawing, the design includes a long, angled wooden box covered with clear plastic glazing and an open bottom and for air intake. Inside the box holds diagonal layers of black metal screen. The vertical drying chamber on top has a back door to access food drying trays inside. The sun radiation passes through the plastic top of the collector box to the absorber screens, which retain heat. Air entering through the intake is warmed as it passes over the absorber screens and then flows into the drying chamber. There, the heated air draws out the food's moisture before exiting through the vents just below the roof. The rising warm air creates negative pressure at the bottom of the collector box, which draws in more outside air to replace the air that left through the top vents. Air will continue to heat and rise, passing through the collector box and into the drying chamber as long as the sun is shining or the dryer has access to another source of heat. As you see, this drying chamber of this dehydrator supports 11 trays to hold up to 10 pounds of tiny sliced food, about 35 to medium 40 sized apples for reference. It can dry this amount of food in 2 sunny days, or about half this amount of food in 1 sunny day because of better ventilation and reduced food mass. The temperature inside the chamber can easily soar to more than 60 degrees Celsius. Until now, we were talking about methods in which the collectors using not concentrated solar energy. When somehow we could concentrate the power, we could achieve higher temperature. In the next couple of minutes, I will talk about the medium temperature solar heat collectors. These collectors produce higher temperatures than the low temperature solar collectors. They are used in drying wood for construction and wood chips as a fuel. These collectors are also used for cooking as solar cooker. These collectors are also used to distill the water in places where drinking water is not easily available. These devices are called solar still. There is a great need to find ways to supply water for the Earth's population. Many countries are facing water shortages and or have residents who use and drink contaminated water. Finding different ways to use our renewable resources, for example solar power, has become an interest. Solar water distillation is the process of using energy from the sunlight to separate freshwater from salts or other contaminants. The basic principles of solar water distillation are simple yet effective. As distillation replicates the way nature makes rain, the untreated water absorbs heat, slowly reaching high temperatures. The heat causes the wet water to evaporate, cool, and condense into vapor, leaving the salt and contaminants behind. Most solar water distillation systems, or simply called stills, are simple black-bottomed vessels filled with water and topped with clear glass or plastic. Sunlight that is absorbed by the black material speeds the rate of evaporation. The evaporation is then trapped by the clear topping and funneled away. Solar stills can be used for low-capacity and self-reliant water supplying systems. Because most stills need to be about 6 square meters in size to produce enough water for a single person for a day. Multiple solar distillation systems are required to produce a large quantity of distilled water. Here you can see a small-scale survival tool. In need of fresh water, you just dig a hole, place a cup in the middle of the pit, cover it with plastic sheet, place a weight over the cup. This has to be the lowest point in the sheet, and wait for the sun. It will evaporate some water, which will condense it and drip into the cup. Now, in the next few minutes, I will talk about an interesting topic. Cooking where there is no electricity is not an easy thing, but many diseases could be avoidable with proper heat treatment. What could be done? There is an easy way to solve this problem: the solar energy. Among the medium temperature collectors, solar cookers are there. They have a lot of benefits. Solar cooking consumes no fuels, wood. Since they are used outside, they do not contribute inside heat, potentially saving cooling costs. Generates no air pollution, no greenhouse gases, and produces no smoke. Cooking smoke kills over 1.6 million people each year, mostly women and children, according to a recent report, and it eliminates fire dangers. But solar cookers have their limitations as well. Solar cookers are less useful in cloudy weather and near the poles. Some solar cookers, especially solar ovens, take longer to cook food than a conventional stove or oven. Some solar cooker designs are affected by strong winds, which can slow the cooking process. But among the possibilities, next to electric, gas, and wood cookers, solar cookers are there. And despite some disadvantages, in some areas, this is the only way. On this slide, you can see approximately how long does it take to cook something in a normal solar cooker. As you see, it takes a bit longer to prepare dinner with solar energy, especially when it is cloudy. For example, to cook a rice meal takes 1.5 to 2 hours, but with free energy. There are two main types of solar cooker. These are the following. On the left side, the box or flat panel type solar cooker, and on the right side, the parabolic solar cooker. First, we will talk about the box or flat panel type solar cooker. A box cooker has a transparent glass or plastic top. It may have additional reflectors to concentrate sunlight into the box. One or more reflectors of shiny metal or foil-lined material may be positioned to bounce extra light into the interior of the oven chamber. The box should have insulated sides. Cooking containers and the inside bottom of the cooker should be dark colored or black. The solar box cooker typically reaches a temperature of 150 Celsius, 300 Fahrenheit, and takes longer time to cook. The parabolic solar cooker is the next in line we will talk about. It is axially symmetrical and shaped so its cross-section is a parabola. The food is kept at its focus for maximum temperature. High-performance parabolic solar cookers can attain temperature above 290 Celsius, 550 Fahrenheit. They can be used to stir-fry vegetables, make soup, bake bread, and boil water in minutes. This cooker can be DIY easily. You just need a parabolic antenna, some metallic foil, and some tools. We will talk about it in a video later in this course. How can you build your own parabolic or box-type solar cooker? On this slide, you can see a large-scale solar cooker. This first application was invented in the USA. It is in production now and is used countrywide on festivals and on other occasions. On this it is possible to cook in tea pans simultaneously. It is time for a short quiz. I have two questions, one about the air heaters and the other about the medium temperature solar collectors. So, what are the pros and the cons of a solar air heater? Pros: they are easy to build, even at home, and there are lots of using methods. The cons: not as efficient as water heat collectors, so you need a bigger unit. The next question: what temperature can be reached in a medium temperature solar heat collectors, and what are the possibilities of using them? Heat between 125 Celsius and 400 Celsius. And you can use them for solar cooking, distilling water, and wood drying. With the quiz, we close the first two topics of this video. From this point, I will talk about the high temperature range applications, which are an intermediate state between this and the next video. So in this video, we are talking about applications creating heat. This type of collectors does the same, but sometimes the heat is further developed into electricity, which is the next topic will be covered in the next video. So we refer to high temperature solar thermal energy to those solar systems that use solar collectors that work at temperatures above 500 Celsius degrees. In this type of installations, once the solar radiation has been transformed into heat energy, the next objective is to transform this heat into electrical energy. There are different technologies to take advantage of high temperature solar thermal energy. However, all solutions are based on the same principles. First, concentrate the solar radiation at point. Raise the temperature of a fluid to increase its internal energy. In this way, energy can be transported. To generate steam to be able to drive, thanks to its thermodynamic properties, the steam turbines and convert the energy into mechanical energy. Operate the electric generators thanks to the kinetic energy provided by the steam turbine. The technologies using the high temperature thermal solar energy, the parabolic through sensors, the tower centrals, the parabolic disc, the Fresnel linear receivers. Parabolic through is a type of solar thermal collector that is straight in one dimension and curved as a parabola in the other two. A Dewar tube, which runs the length of the throw at its focal line, acquires heat from it. The system is usually aligned on a north-south axis. The mirror is oriented so that sunlight which it reflects is concentrated on the tube, which contains a fluid which is heated to a high temperature. Depending on the solar application and the temperature at which you want to reach, one type of fluid or another is used. For a maximum temperature of 200 Celsius degrees, the mineralized water or ethylene glycol can be used as working fluids, and for higher temperature up to 400 Celsius degrees, synthetic oil are used. The overall efficiency conversion is 15%, and the maximum temperature are about 400 Celsius degrees. Let's see the components of a parabolic tube. First, the collector is essentially a parabolic mirror or reflector used to concentrate light on the single point made of borosilicate glass or polymer lined with silver. Then the bearing structure to carry wind loads and weight of the contractor, and the receiver. To obtain an optimal energy performance, this type of concentration sensor must change its position, adapting to the position of the sun by turning around the axis parallel to its focal line to take advantage of direct sun radiation. So, in the bearing system, there is a tracking engine mounted. The second type of high-temperature solar collectors are the dish Stirling. It is a solar-powered Stirling engine which receives its input power from the concentrated heat of the parabolic dish. The fluid located in the receiver is heated to a temperature of more than 750 Celsius degrees, thereby obtaining a certain heat energy. The thermal energy obtained is used by the Stirling engine or the microturbine to produce electricity. It has the following components. The concentrator. It is not single parabolic dish, as it is difficult to manufacture and assemble. This engine used separate mirrors mounted on the dish. The material is usually glass, but fiber resins are also used. Tracking system. Tracking system works such that there is never a shadow over the concentrator, which reduces the collector efficiency. Thus, it has a two-axial tracking system. Horizontal and vertical movement of the concentrator are actuated with the help of servomotors. Receiver. The receiver is the link between the concentrator and the Stirling engine. It is of two types: solar-only receivers, which only operates during the daytime, and the other is the gas burner type to provide power in the night. The rest of the part is the Stirling engine. A Stirling engine is not a common engine, so I try to explain it on this slide. A Stirling engine is a heat or external combustion engine that is operated by cycles, compressions, and expansion of air or other gas, actually the working fluid, at different temperatures, resulting in a net conversion of heat energy to mechanical work. Let's see how does it work. First, most of the working gas is in the hot cylinder and has more contact with the hot cylinder's wall. This results in overall heating of the gas. Its pressure increases and the gas expands. Because the hot cylinder is at maximum volume and the cold cylinder is at the top of its stroke, minimum volume, the volume of the system increased by expansion into the cold cylinder. 2. The system is at its maximum volume and the gas has more contact with the cold cylinder. This cools the gas, lowering its pressure. Because of flywheel momentum or other piston parts on the same shaft, the hot cylinder begins an upstroke, reducing the volume of the system. 3. Almost all the gas is now in the cold cylinder and cooling continues. This continues to reduce the pressure of the gas and cause contraction. Because of the hot cylinder is at a minimum volume and the cold cylinder is at its maximum volume, the volume of the system is further reduced by compression of the cold cylinder inwards. 4. The system is at its minimum volume and the gas has greater contact with the hot cylinder again. the volume of the system increases by expansion of the hot cylinder. An alternator coupled to the Stirling engine takes advantage of the movement generated by the engine to produce electrical energy. The electricity generated by this renewable resource can be connected to the electricity grid for sale, or in most cases, it can be used for direct consumption. On this slide, you see the solar tower. This solar thermal system is based on the concentration of solar radiation towards a point in a tower. It is also known as central receiver systems. The tower systems are formed by the field of heliostats, actually mobile mirrors on two axes. The heliostats capture and concentrate the solar radiation on a receiver installed at the top of a central tower. The operation of this type of renewable energy plant is simple. The central solar receiver generates steam at high temperature. The generated steam is subsequently used to move a steam turbine. Thanks to the steam turbine, mechanical work is obtained in the form of kinetic energy and axis in rotation. And thanks to an electrical generator attached, the energy will be converted into electrical energy. It is often coupled with a thermal energy storage system to store the heat energy. This energy can be used in nighttime to produce power. It is often coupled with a thermal energy storage system to store the heat energy. This energy can be used in nighttime to produce power. Let's see the parts of a solar power tower. The collector system. It contains the collector field and heliostats that redirect and focuses the sunlight on the receiver. The major system elements are two-axis tracking mirrors. The receiver. It is a cylindrical tube wall heat exchanger that heats molten nitrate salt from 290 Celsius, 550 Fahrenheit, to 565 Celsius, 1050 Fahrenheit. Thermal salt storage. One of it stores high temperature nitrate salt, 565 degrees Celsius, from the receiver for use by the steam generator, and the other one stores low temperature nitrate salt at 290 degrees Celsius from the steam generator for use by the receiver. The steam generation system uses thermal energy from the hot nitrate source to produce superheated steam. Concentrated solar power systems have until recently focused on bulk electricity production, with the main focus on solar towers and stroke-type collectors. Recent developments have focused on smaller units to supplement thermal power stations and to provide heat for industrial processes. Collectors based on the linear Fresnel reflector design are leading the pack. The Fresnel linear reflector is a system of concentration of solar radiation similar to parabolic through mirrors. In this case, these linear solar collectors carry normal flat mirrors and simulate the curvature of parabolic through mirrors, which are more expensive by varying the angle of each row with a single tracking axis. The main advantage of the Fresnel linear receiver system is its simple installation and its low cost, although the energy efficiency is lower than the parabolic cylinder collector technology. The linear Fresnel reflector technology receives its name from the Fresnel lens, which was developed by the French physicist Austin Jean Fresnel for lighthouses in the 18th century. The principle of this lens is the breaking of the continuous surface of a standard lens into a set of surfaces with discontinuous between them. This allows to a substantial reduction in thickness and thus weight and volume of the lens, at the expense of reducing the imaging quality of the lens. The mirrors focus the sun onto a receiver which contains the heat transfer medium, which could be water, oil, or even molten salt in some designs. The heat transfer medium used will depend on the operation temperature of the system. In the first two Trog systems, the whole structure rotated about an axis coincident with the focal point of the tube. This means that the mirrors and the collector are connected mechanically, requiring bearings through which the collector tube must pass. In the Fresnel system, the individual mirrors rotate to track the sun. There is no mechanical connection between the mirrors and the collector. Separation of the mirrors and the receiver allows high-temperature heat transfer mediums to be used, and also a much wider scope in the design of the receiver. The Fresnel system also allows individual control of each mirror, effectively changing the configuration of the reflector to optimize its function. After finishing the high-temperature collectors, it is time to assess your knowledge about them. So, what temperature can be reached in the high-temperature solar heat collectors? Above 500 degrees Celsius. What type of high-temperature solar heat collectors were we talked about? Parabolic through Stirling solar power tower, and finally the Fresnel reflector. We will discuss today the solar air heaters, the medium and high temperature range collectors. In the next video, my colleague will talk about the conversion of solar energy into electricity. So, see you next time. Bye.